Yo solo estuve la última vez con ellos en Australia hace 4 años, pero desde entonces han vuelto a Reino Unido. Sandy está en Reading y Colin está en el Imperial College. Y bueno, pues va a hablar primero Colin más de temas de captura de CO2 y en secuencias de paleo, y luego Sandy más sobre modelización y su relación con algo de dendro, que es uno de los principales intereses ahora dentro del proyecto del PMIP sobre modelización paleo. Y lo que os comentaba, pues cualquier interés que puedan provocar, pues van a estar por aquí unos días con nosotros hasta el miércoles de la semana que viene. So thank you for coming. First is your turn, Colin, and after Colin it's Sandy's time. Thank you very much.
Okay, well, I'm Colin Prentice, and my salary is very kindly paid for by the AXA research firm. AXA is the world's second largest insurance company, apparently, and they have a research fund, and, well, they fund me, which is good. So, this is the fundamentals. It's all here, really. The photosynthesis, the standard form of photosynthesis by C3 plants, which includes virtually all trees, for example, it increases with increasing CO2 concentration. Now, the value of the last phase of maximum, about 180 parts per million at the lowest, is almost a starvation level, actually quite hard for trees to survive at that level. And the present, I put that wrong. I said it's 440. It's not 440. It's only 400. Sorry, but not yet. We have to wait another 20 years or so. But the present value of 400 ppm is actually not saturation level. So as you increase it further, then there is a further increase in photosynthesis. And experiments, there have been many experiments of this type, free air carbon dioxide enrichment experiments. In every case, they show increased photosynthesis when the CO2 level is boosted from, say, 400 to 500 or 600. They always show increased photosynthesis, even if that doesn't in every case translate into plant growth. I'm not going to go into that aspect much, but Sandy will touch on it later. Now, another thing that changes is the water use efficiency. So, using the standard symbols here, A for assimilation. Oops. A for assimilation, and E for transpiration. So A is carbon uptake, E is water loss by plants. And this ratio always increases with CO2. And this can be measured in practice using the delta C13, so the stable carbon isotope composition is a very good indicator of the ratio of the leaf internal CO2 to the ambient CO2, and as I'll explain in a minute, that tells us about the water use efficiency. And interestingly, and a lot of people don't seem to know this, but the water use efficiency increase doesn't have any saturation level. So, you know, if CO2 was 1,000 ppm or something, we would certainly have no further increase in photosynthesis, but the water use efficiency carries on increasing. And so, if you go back to earlier geological times when CO2 has been as high, at least as high as 2,000 parts per million, during those times, plants had almost no stomata. They didn't really need stomata. No plant wants to use any more water than necessary, and the CO2 would just, you know, just pour in through a very small opening. So water use efficiency always increases with CO2. Now, a key point of my talk is that when CO2 is low, therefore the plants are very inefficient. They need to use more water for less growth. So that was the situation during glacial periods. And this situation also favours C4 plants, especially in hot and dry conditions. So tropical grasses, quinopods and so on are directly favoured by low CO2. And I'll argue that the CO2 change has a major effect on vegetation composition and structure. Okay, pay attention to this. The test at the end. This is the standard model of photosynthesis as developed. Most of this was developed by Graham Farquhar, Suzanne Boncameron and Joe Berry, and published in 1980 in a paper that is one of the most cited in all of biology, because this is a model that actually is correct. It actually works. It describes C3 photosynthesis, and what this says is that First of all, there is a biochemical limitation to the rate of photosynthesis. The rate of photosynthesis is equal to the lesser of these two quantities, AJ and AC, minus the dot respiration. That's dot respiration is small, I won't mention it again. So these two are, one of them is related to light, this I-abs is absorbed light, and the other one is related to the amount of the main carbon fixing enzyme, ribisco. So this is determined by light, this is determined by enzymes, but this thing here, CI, that's the leaf internal concentration of CO2. So that's the concentration that is actually getting to the chloroplasts. So you see, these are both hyperbolic relationships. They're saturating relationships like this, and both. So whether this limitation is operating, it tends to under low light, for example. This tends to be working at midday. But either way, there is a response to CO2. It's not quite the same response, but it's a response. And in practice, it was understood from the beginning of this modelling development that these two are usually approximately equal on a daily average. So they're usually co-limiting. Now, that's the biochemistry. But what governs the leaf internal concentration of CO2? Well, one thing that governs it is photosynthesis, because photosynthesis is drawing down the CO2, so there's always less CO2 in the leaf than there is outside the leaf, but there's also a diffusional limitation. That's the rate at which CO2 can get into the leaf, and that's determined by the stomata. So that is a diffusional limitation, and that's just a diffusion equation. It says that as well as being equal to this, photosynthesis is also equal to this, stomatal conductance, which depends on the number of stomata and the extent to which they're open or closed. Ca, which is the ambient concentration, and then this factor here, 1 minus chi, and chi is this ratio of leaf internal to ambient CO2. Now, when the stomata are open to let CO2 in, they let water out. So the two things have to go together. So we can also write an equation for transpiration, which says that the transpiration rate is equal to 1.6 times stomatal conductance times the vapor pressure deficit in the atmosphere. So the dryness of the atmosphere, that's the pulling power for water. And stomatal conductance, so appears again, but there's a 1.6 because water is a smaller molecule, so it diffuses faster than CO2. So from these two equations here, we can also write down what the water use efficiency is. It's very, very simple. It doesn't depend on the stomatal conductance. It depends only on this number chi, that actually doesn't vary very much. On the vapor pressure deficit, so how dry the air is, so the drier the air, the less efficient the plants are, but also the CO2 concentration, so the more CO2 is in the air, the more efficient they are. So that's the basics, and this is just putting it in graphical terms. You see here, you could do this. Experiments have been thousands and thousands of times. If you have the instrument that measures photosynthesis, here is the CI, so you can manipulate that by changing the CA, ambient CO2. This is the assimilation rate, and you get a curve that looks something like this. So at low CI, it's following the ribisco limitation, crossing the co-limitation point and going up into light limitation up here. But at the same time, there is a diffusion limitation, which can be written like this. It can be drawn like this, and this point here is the actual rate of photosynthesis at any one moment. This is the actual CO2 concentration in the leaf, and that's the assimilation rate. Now, this number, it can be considered to be an exchange rate between CO2 and water. It's quite conservative, it doesn't vary much. Between about 0.7 and 0.8 is a very common value for C3 plants under mesic conditions, but there is some variation. It does vary with aridity, temperature, and atmospheric pressure. As I mentioned, it can be inferred from delta C13 measurements on leaves and also tree rings. We've worked with a very large, several thousand data set globally distributed of delta C13 on measurements for leaves. This is at the moment only published as a preprint, but we've tested a predictive model for this quantity. And to cut a very long story short, the model works. There's quite a bit of scatter, but we can correctly predict the typical
CI/CA ratio for different plant types, as you see here. But the key thing is that it's different for different plant types just because they grow in different environments. So this is entirely predictive from the environment. We don't need to consider any differences among trees and shrubs and grasses, evergreens versus deciduous. They all behave the same way because they all obey the equations of C3 photosynthesis, which is convenient. So, on to paleoecology. There are three ways in which delta C13 is used, at least three ways. One has to do with the fact that there is a discrimination in photosynthesis. So the way it works is that as CO2 comes into the leaf, the C12 actually diffuses a little bit faster than the C13, and then when photosynthesis happens, then that happens a lot faster for C12 than for C13, and that is the key mechanism that influences the delta C13. There is also, so basically terrestrial biosphere carbon always has a very negative C13 signature, always is depleted in C13 compared to C12. There's a large difference in the signature for C4 and C3 plants because the C4 photosynthesis works in a different way, has much less strong discrimination. And finally, there is variation within C3 plants, which is related to climate and also to altitude. So, getting on to an actual example here, this was apparently a very influential paper and seriously misleading, published by Huang et al. In Science in 2001. I think a lot of people read this and thought, oh, we don't need to worry about CO2. So, what this is, that was the best available CO2 record at the time, but it's about right. So showing the low level glacier maximum and then gradually rising up into the Holocene. This is a record from tropical southern Mexico, and this is a record from temperate northwestern Mexico. And the point made by this paper was that if CO2 has a profound effect, as I say it does, then you should always see C4 dominance in the glacial periods giving way to C3 dominance in the interglacial. So that's what you see here, and what you see here is the opposite. So C3 was dominant in the glacial period, giving way to C4 in the interglacial period. Now the reason for this is it's not either or. You know, if CO2 has an effect, climate has an effect too. Here there was a massive change in climate. So this is the western seaboard of North America, where there were huge glacial lakes and so on, with massively greater precipitation at the glacial maximum, and that gave way to the semi-arid environment we see now. So, in other words, this paper was claiming that this pattern disproves the CO2 effect. It doesn't. Some evidence that CO2 influences vegetation. Paper by Sandy and myself some time ago showing that the extent of forest reduction globally at the last glacial maximum is far greater than can be explained by climate change. There is present evidence, so-called woody thickening, which is observed in savannas all over the world and has been observed over the last 50 years or so. An increase in the density of woody plants, shrubs and trees, at the expense of grasses. So their C3 plants are taking over at the expense of C4 grasses in the savannas. There's experimental evidence also to show that this works. This phenomenon can be caused by CO2. A paper appeared in 2011 in Nature Geoscience claiming that the idea of a moving IPE-CSIC was all wrong in the Holocene. Between the glacial maximum, between the glacial and the Holocene. And because they said the effect was zonally symmetrical, the vegetation changes were zonally symmetrical. Well, another interpretation is that the effects that they were looking at, big shifts between C3 and C4 vegetation in Africa, were in fact due to CO2 and not to climate, which was a factor that they didn't mention in this paper. We did a study some time back showing that it's actually based, this was done in collaboration with the late Jeff Eglinton, working with marine cores here, and these were C13 analysis on leaf waxes that have been blown. The prevailing winds are always this way, so it's in the very southern tip of Africa. so basically blown across the continent. So we did reconstruct what their catchment areas were and so on. But the story basically, these are very low resolution chords, so this is just 2 time slices, Holocene and Glacial maximum. The blue being the Holocene, the red being the Holocene, the blue being the Glacial maximum. You see a divergence along this transect, so as you get up to the more northerly part here, that implies that a lot of these areas of forest were actually savannas or grasslands at the time, dominated by C4 plants, and hence the change in the C13 signature. We modelled this using the 5 and 4 model. The data here, this is the difference in C13, so the data is shown with the black line there, and the red line is what happens if you apply last glacier maximum climate, as simulated by several PMET models. You get this. In other words, you don't get the observations if you apply the changing climate, but then you tell the model about CO2 and you're almost spot on. So, does CO2 influence vegetation? Simple answer is yes, but the point is both climate change and CO2 influence vegetation. Large regional climate changes can certainly overwhelm the CO2 effect, so you need to consider both. But nonetheless, if you statistically reconstruct a past climate based on past vegetation, then you need to consider the CO2 effect. So in other words, you need to build in a correction. If you don't, glacial climates will always appear to be more dry than they actually were. I keep hearing stories like this. I heard 2 of them at the Pages meeting. People being very puzzled and coming up with convoluted explanations for why you could have high lake levels accompanying very sparse vegetation. True in much of the Mediterranean region, for example. So why is that? Well, the lake levels are responding obviously to changes in precipitation and evaporation, whereas the vegetation is also responding to CO2. It's a simple explanation. So how can you do the correction? Well, there's basically 2 approaches that have been tried. One involves taking a complex process-based model and inverting it. This is a rather tedious procedure, so it's never really caught on. It's only ever been, done by the people who did it, so to speak. It's not very transferable.
Engine's still doing it, and there was a poster at the OSM.
Oh, was there? Oh, all right. Okay, some people. All right. Okay, good.
Still
Right.
doing it.
So, and I think this paper is the one describing it first, but it's interesting. It yields reasonable looking results. It does, among other things, it deals with a problem that was encountered in statistical reconstructions of Mediterranean vegetation at last glacier maxima that seems to be coming out with analogues somewhere in the steppes of Central Asia. So maybe yes, that's what their analogues were, but when you take the CO2 into account, then you get much more reasonable estimates of even changes in winter temperature, for example. It's model dependent. You've got, these models have a lot of plant functional types in them, which are all parameterized differently. Inverting it is a problem because it's dependent on on-off switches, whether you have this type or that type. So, so there are problems with this. An alternative approach, which we developed, was that you do a statistical reconstruction, you do it however you like, but you can then do a second step where you actually make a correction. And we have a paper now on this. So I was the lead author on that, but Sandy's involved too, and this is currently being sort of moved forward by a student of Sandy's. You use any statistical method and then make the correction, and the point is this is using some of these quite general equations of photosynthesis and transpiration. It's a proof of concept, the paper. I wouldn't advise anybody to use the method as described in the paper. It's really a proof of concept, it's being further developed, but it was tested out in Australia, because we were in Australia at the time. A new data set that Sandy and others have been putting together uses a particular method of statistical reconstruction, which I'm not sure I recommend this either, but it would seem like a good idea at the time, which involved classifying species into plant functional types, distributing the membership in ambiguous cases, because obviously some pollen taxa might belong to more than one type, and then fitting quadratic surfaces to the relation between abundance of plant functional types temperature and a moisture index, which is just the ratio, basically the ratio of precipitation to potential evapotranspiration. It uses a maximum likelihood method to reconstruct these values statistically. That's just showing the surface data set, training data set, the LGM data set. That's what the recent climate of Australia looks like, and you get surfaces like this for different functional types, and in the end make a maximum likelihood estimate using those fitted functions. So that's just a particular way of doing statistical reconstructions. There are many others, of course. Now, when you draw it all out like this, it's a bit scary, you know, everything seems to influence everything else. So here we have the moisture index and the temperature, but then, you know, you influences net radiation, precipitation, actual evaporation, potential evaporation, a measure called delta E, which is related to aridity, eventually influencing chi, and then chi and CO2 concentration, affecting a quantity which I'm calling the water use inefficiency, and the ratio of E to A. We could have done it with water use efficiency, but somehow this seems to be make it a bit easier to understand what we're doing. Now, in principle, the relationship between this water use inefficiency and the moisture index, obviously that relationship can be affected by the moisture index itself, but also strongly affected by the CO2 concentration. Now, when we look at that web of, entangled looking web of interactions, and we see that there are other things could have an influence too, but we did consider those. Don't seem to be too important. So basically we end up solving an equation, and this did require a mathematician to do it, but the equation is to calculate something called delta M, which is the correction. So it's the real moisture index, or our best estimate of the real moisture index, minus the reconstructed. So it's a correction that we apply to the reconstructed. And the idea is to solve this, is to find that value such that the environment, well, I always find this difficult to put into words. There's an equation for it there, but the idea is that the plant of course knows about CO2, but our reconstruction method doesn't. So we have a reconstructed value that is not reliable. However, we assume that what the plant really knows about is its water use efficiency. So we recalculate the water use efficiency with knowledge of this CO2 concentration. And this is from the paper showing that the correction in terms, because it depends on the actual reconstructed value, so as you get to high values then you get larger corrections, not surprisingly, but it also depends on CO2 and becomes large as the CO2 gets low. This little triangle, that's actually a space where C3 photosynthesis is actually impossible. So if it's dry enough and the CO2 is low enough, then C3 plants can't survive at all. And we could do this as a sensitivity measure to various things, and a couple of long stories short, it's far more sensitive. This calculation is very sensitive to CO2 and not very sensitive to other things. And we applied this to create, and this is a reconstruction of temperature changes, LGM, to reason. This is uncorrected moisture index, it's corrected, and you see a lot more blue over here, and particularly an area that did actually have very active rivers and high lakes and so on. Everything is getting more blue, so this is bringing the pollen evidence into line with paleohydrology evidence. It has an effect on the implied value of this internal CO2 concentration. If you actually believed the statistical reconstructions, you'd be getting dangerously low CI down here, about 60 ppm, but after the correction you're getting much more plausible CI is about twice as large. This blue here, again, is the actual survival limit for C3 plant. And just a final example, published 6 years ago in New Phytologist. This is done with paleoclimate models and vegetation model, the LPX model, just showing simulation, consensus simulation from four last galaxy maximum simulations. This is data here, so biomes reconstructed from pond data at the bottom, showing the browns and the yellows are basically are non-forest vegetation. So you see big reduction in forest area compared with present, and this is the simulation here, which also shows that big reduction in forest area. But the point is, it needs the CO2 to do it. With these simulations, we also calculated, well, the land area doesn't really change because the continental shelves were bigger at the same time the ice sheets were there. Gross primary production down by a lot. Net primary production down by a lot, and there is independent evidence for those things. Carbon storage also down by a lot, and that is broadly consistent with some other evidence. But the point is that these effects are essentially caused by CO2, they're not caused by changing climate. So my conclusions are CO2 does have a major influence on primary production of land and on carbon storage that is additional to the effects of climate. Tropical forest area and the global primary production at the last rate of maximum are much less, mainly because the CO2 is low. And today, given that we can see this phenomenon in the paleo data, it seems reasonable to assume that's what's happening now, and that the increasing tree cover and the increasing gross primary production, for which again there is independent evidence, are mainly caused by the rate of rising CO2 rather than by the changes in climate. So this is a case where, if you like, paleo data can, or analysis of paleo data can be informative about what's going on now, but paleo kind of reconstructions also can benefit from our understanding of plant physiology. Okay.
So I'm going to continue this theme, and what I'm going to talk about is understanding and modelling the tree ring records. So, you know, you're all familiar with the fact that people go out there, they take these cores, woo, don't touch the screen, Harrison. No. And then, you know, the thick rings are supposed to be times when the tree was having a good time, and the thin rings are the times when it was suffering from drought and things like this. What I'm trying to do is to apply some ecological thinking to interpreting these kinds of records. And that's very important because the tree ring, as you know, one of the things that people are doing, they're doing climate simulations of the last millennium. It's really important because that's the time period that enables us to distinguish, as we go into the future, the impact of humans since the, so it's a detection of climate change caused by humans and separating that from natural climate variability. So here's a whole bunch of simulations that people have done for the last millennium to try and diagnose this human impact on the climate. And here are the tree ring, well, here are the climate reconstructions for the northern hemisphere of the last, northern hemisphere last millennium reconstructions. And you can see that the different reconstructions have very different patterns. And when you then try and use, so here's the reconstructions here are the climate model simulations, you're trying to use these reconstructions to say which of these simulations is better, right? Either because it's got the right forcing, climate forcing, or because it's a better model. And then you say, well, I can't discriminate between the models because there's so much uncertainty in these reconstructions. Now, a huge part of those reconstructions are based on tree ring reconstructions of climate, statistical reconstructions of climate. And so if we can't discriminate using what is our best distributed, best method, it poses problems for understanding the future climate change. So, in tree ring, this is Tree Rings 101, which is where I'm at. You know, what happens? You have a tree ring series like this. You make a correlation with observed climate at your site, and then you assume that so here's quite a nice correlation. The red line's the observations, and the blue line is your tree rings. You've got your correlation, and then you say, well, that correlation is going to hold all the way back through time, so I can simply use that correlation to say what the climate is. And depending on what your site is, it might be summer temperature, it might be moisture, it might be river runoff. I've seen that. I've even seen the reconstruction of cloudiness and so on. So you just pick your favourite climate variable and make that correlation. So you make these various assumptions when you're doing tree ring work. So the first thing you're making an assumption is that you can remove the effect of ontogeny, aging, effectively growth, by doing some kind of statistical smoothing of your curves. You make the assumption that usually a single factor is controlling tree growth. And secondly, that factor is stationary through time, through thousands of years. And then you say, well, non-climate factors, like the CO2 that Colin's talking about, have absolutely no effect on growth of trees. And then you also make a fourth assumption, which is that when you change tree productivity, every single bit of the tree changes in the same way. You increase the amount of leaves, you increase the amount of stems, you increase the amount of roots, and you increase it in the same fashion. And I want to look at those assumptions because I don't think any of them are right. So here's ontogeny. There are multiple statistical methods to take out the growth effects on tree rings. They all assume that it's some kind of aging, that rings get smaller as trees grow older. Here are just 5 of the methods that are currently used in Five of the methods that are used in dendrochronology, and you can see certainly in the early part they have a huge impact, that even when you go back, after hundreds of years of tree growth, depending on which method you use, you're going to get very different results. Now, one of the points here is that this is always talked about in the dendro literature as tree growth and aging. It's never thought about in terms of tree growth and size, and I want to return to that in a minute. Okay, stationarity. Assumption of stationarity. Here are all of the Picea records from the International Tree Ring Database covering the period from 1940 to 2000. They all cover that same period. What my colleague Li Guangqi has done is to correlate all of those records with summer temperature for the first period, 1940 to 1970. And the reds mean strongly positively correlated with summer temperature, and the blues mean strongly negatively correlated with summer temperature, and the wishy-washy colours in between mean I can't find any correlation. And so what you see is that there are maybe 20 or so sites in this Northern Hemisphere data set that show a strong positive correlation over this 30-year period with summer temperature. But there are almost an equal number of sites that show a negative correlation with summer temperature, and a lot of them show no correlation at all. Now, if you then take those same sites, or at least you take the ones that are strongly correlated, the red ones here, so here's the strong correlation in the first period, and you look what happens over time, in the next 30-year period, they become totally non-correlated. Right? So as you move from 1970 to 2000, suddenly all the pattern of temperature correlations in these sites has disappeared. And during that time, in fact, the correlation with precipitation increases. But when you're making your dendro reconstructions, you're just assuming this. And you can see this is the same set of sites, except now we're looking at 30-year intervals, so moving 30-year windows, and you can see here's strongly correlated, and they lose correlation, they lose correlation, they lose correlation. But the strength of the correlation does actually vary in each of those 30-year periods. So, and it turns out that if you then look at that second period, you can see some other sites suddenly become strongly correlated with temperature. So this idea of stationarity is absolutely not real. Climate and the relationship to climate, trees' relationship to climate does not stay stationary through time. Now, actually people have known about this, the tree ring community have known about this for some time, but it's part of the dirty linen. So I'm sure you've all heard about this so-called divergence problem. It's what caused ClimateGate. Okay? No, truly. Because when tree ring people were making reconstructions of Northern Hemisphere temperature, and they've got fairly nice correlations during this early part, and then round about 1960, 1970, those correlations apparently fell apart. The records diverged. So this is the actual observed temperature, this is the reconstructed temperature, very big differences, and they kind of said, okay, let's just not use that data. And unfortunately, someone leaked the email and did cause a fuss. And the literature is now full of various explanations. So, yes, well, this is kind of like a this has randomized itself. So, the explanations go, well, actually, temperature was limiting, and now it's increased, so it's no longer limiting, so that's why there's no relationship. Okay. Or, hey, maybe it's CO2 fertilisation suddenly switched on. Or, okay, when we've got this warming in the northern polar area, we have a marked shift in the amount of diffuse to direct radiation, and diffuse radiation is more effective for photosynthesis, so maybe this is actually a diffuse radiation signal. Or maybe actually it wasn't temperature that was the control, maybe temperature was controlled to, I don't know, spring frost or moisture or something, and so we had a strong correlation during the early part and it disappeared. But all of this has been hand-waving to try and get around this problem of not having a stationary relationship through time. So Colin mentioned the CO2 impact, and I wanted just to return to this again. This is a study, and there have now been several studies. So this was a study of tropical forests and tree growth, looking at the CO2 impact in these tropical forests over the last 150 years or so. And what they're showing is that they are getting changes in CI, so the internal concentration of CO2, which therefore implies changes in the amount of photosynthesis. This is water use efficiency, so they're getting increases in water use efficiency, but apparently no change in tree growth. Tree growth as measured by radial stem diameter. And one of the explanations that's been put forward to that is that tree growth is not the same in all components. So what we know from experimental work in FACE, for example, is that as you increase CO2, so you get an increase. So here's ambient CO2 through time. Here's an experiment with, this is actually several years, several years worth of elevated CO2, and what you see is an increase in fine root mass here, and here showing an increase in coarse root mass. So there's a lot of evidence that as you increase CO2, you get a bit of an increase in leaves, but a huge increase in roots, and that therefore the balance of carbon that's going into roots and stem and leaves is changing through time. So changes in allocation can also be important in terms of understanding this CO2 response. So now what I want to do is to introduce you very quickly to a tree growth model. I've put my obligatory, or his obligatory equations down there. You don't have to worry about it. Essentially, what this is the photosynthesis model that Colin was just talking about here, the P model. You only have to wave at it and it goes mad. Okay, the P model, which is basically running with temperature, precip, fractional cloud cover, CO2, but it knows about latitude and it knows about elevation because that's affecting the amount of light you're getting. That predicts how much GPP, so gross primary productivity, you have. This goes into the T model, the tree growth model, which is based on allocating carbon between those three pools, leaves, stems and roots, and uses well-known functional geometry relationships to do that, to partition height versus width growth. And so that gives us simulated ring width at the end. And I have to say that this model, one complication about this model is that you do need to give it a number of species-specific parameters, like what is the crown area, what's the relationship between height and diameter growth, how much root respiration is there. But it's a relatively limited number of parameters, many of which can either be measured in the field or available from the forestry literature, so it's relatively easy to use. And we've applied it to these, this is the pretty picture bit, to these 4 sites so far. So Pinus coriensis in Chiangmai Mountains in China, Juniperus columularis, I think, from western USA, California, Calitris from the Great Western Woodlands in Australia, and we've just been applying it to Cedrus atlantica in Morocco. So different regions, different kinds of climate, different kinds of conifers. So let's just look at some of these assumptions and how this model would deal with the tree relief assumptions. So first of all, the aging. So a nice aging curve here for our trees. What we do in the simulations is we initialize each tree from its birth date giving it its actual diameter. So we, in fact, started these simulations in 1958 because that's when we had the climate data, and we started each tree with its different diameter at that stage. It turns out that on this particular site we have had a few trees that were younger than 50 years, we had a group of trees that were between 50 and 100 years, and we had a much older cohort, and that's important, as I'll show you in a minute. But at any one tree, we can simulate a growth curve that looks like this. So rapid growth initially, and then it slows down and it gets slower and slower through time. This does not look like the curve that statisticians put through their tree rings. They're using something that's like this, so they don't get that first peak, for example. So it's a very different ontogeny in the model world. Now here we've been modelling those three cohorts I talked to you about, so the young ones, middle-aged ones and old ones here. And the observations are in black, the average of all of the trees in the site are in black, and our simulations are in blue for each of those. And what you see for this is that we're basically, with this very simple model, able to simulate the average level of tree growth on the site, and also the interannual variability. And the statistics are about the same as people get for statistical correlations that they've chosen. But we've also then been able to look at what happens to these different cohorts. And this was a very radical test. So on the top here, this is the observed average size for the three cohorts, and the bottom is our simulation. Now, for some reason, this middle-age cohort, you'd normally expect highest rates for the young trees, intermediate rates for the middle-aged trees, and low rates for the old trees. This is not what we see here. We do see high rates for the young trees, but for some reason this middle-aged cohort must have had a very rough first 50 years, and it was growing slowly all of the time. And once you start growing slowly, you keep on growing slowly. So, you know, they have much lower growth rates, and the model is able to reproduce that because the model knows that growth is affecting, that growth during your young period affects how you do in the old age. This would not show up if you did a standard dendrocorrection. The other thing the model is able to do is to reproduce the multiple controls on tree growth. So here, this is a GLM analysis of a number of different potential climate controls on tree growth. The top panels show the observations, the bottom panels show what the model does. Remember, the model is always going to be less noisy than the observations because there are other minor factors that are around. But essentially, both the observations and the model show strong correlation, strong positive effect of increasing light, R, a negative effect of vapor pressure deficit, so atmospheric dryness, because when the atmosphere dries out, your stomata close, and if you're a C3 plant, you can't photosynthesize, and a strong positive effect of soil moisture, alpha, because again, if you have lots of soil moisture, then you can continue to keep those stomata open and continue to photosynthesize. So model and observation give you a nice evidence of multiple controls on growth through time. Okay, let's move on to Calitris in the Great Western Woodlands. This is the Great Western Woodlands. It's very famous because it's the driest place that you've got eucalypt trees. So you have these big, huge eucalypt trees there. And growing underneath them are these scrubby Calitris things. But the Calitris can live, you know, 100, 200 years, and therefore, and is a survivor basically in this environment.
Excuse me, Sandy, what is Calitris? Is conifer? Or
It's a conifer, yes. Calitris, what's its closest relative?
It's
a bit like a juniper.
Yeah, it's
cupressaceae. It's cupressaceae, that's right. So it is like a juniper, and it has those nice long needly wands. Okay, so we start off here. We're doing our simulation again. The simulation's in blue. The black is the mean of the observations, and you see the range of the observations. And we were quite pleased that we got the mean level correctly. We get the interannual variability reasonably correctly, but you can see here's the divergence problem. So observations suggest that the tree growth is dropping off, and we're predicting that it should be surviving. So the trend in this is wrong. Now, we also then can look at the climate, and again you see at this site both observations and models show strong positive relationship to light, strong negative relationship to atmospheric drought, strong positive relationship to soil moisture. But then where it disagrees is what's happening with CO2. So the model is showing a positive relationship and a significant relationship with the CO2, and the observations are showing no relationship to CO2. So then you say to yourself, well, how can this possibly happen? Now we've got a model. So we can look at what happens to allocation. Our allocation is controlled by ratios between, so we have a ratio of how much root to how much leaf, and a ratio of how much root to how much tree stem, and we can say, okay, we've got to match that record here. Let's see if we can do that by changing the allocation as CO2 changes. And this is that tuning that we've done. So basically what we've got in here is the CO2 record. This is alpha, soil moisture over that time. And here's the tuning that we would have to do in 30-year windows to reproduce the tree ring record. And what you see here is that you can reproduce the tree ring record if during the first period it's probably drought, persistent drought, that's causing the change in the tree ring widths. But certainly here, this change in CO2 is what's driving the change, because it's more allocation underground to the roots in order to be able to get nutrients and water to sustain that increased productivity. So if we look at the changes, we can divide it into about 70% signal of changing CO2 over that period, and about 30% signal of changing soil moisture. Okay, so we can then go back and look at this question that Colin was looking at, which is, at the last glacial maximum, with low CO2, how did trees survive? And we looked at these famous sites of glacial junipers from the La Brea tar pits in California, where they've done the isotopic measurements, and they show that the glacial ratio of Ci to Ca, internal to external CO2, is the same as today. So if it's 180 ppm, the internal concentration is about 90 to 100 ppm, and as Colin pointed out, that's really close to starvation point. But they were measuring tree rings on this, and the tree ring widths are the same at the glacial as they are today. Right? Okay, so how can you explain that, guys? Right? So we can show in our model, here's the observations of CICA, here is our model, and the red dots are the present day and the blue dots are last glacial maximum. At all elevations in our model, we get the same CICA present and last glacial maximum. So we're able to reproduce that part of the equation, which means our photosynthesis part, our productivity part, is correct. And so if we want to get the tree rings correct, what we have to do is to change the allocation to leaves and to roots. So this is the allocation to leaves, so crown area, leaf area index in the crown. And this is the allocation to roots. And what we've done is a series of experiments where we've dropped CO2, we've kept LGM climate, everything's exactly the same. LGM GPP is going into this, but we've dropped the CO2 sequentially and asked what do we need to do to these allocation measures in order to maintain tree ring. And you can see ring widths. So what you can see is that you have to drop leaf area index by about 10% in order to do that, and you have to drop root area by about 30% in order to do that.
Can I make a question right now?
Yeah.
Before I forget. We are allocating carbon to roots. I mean, trees can do roots, can do branches, stems, but they can also do fruits and flowers.
I haven't got that yet. No.
Okay. Because
no.
I'm thinking right now that is going to massively change the pollen productivity too. And that's flowers.
yes, it will change. I think it will change pollen productivity, and that's why we're thinking about these PPEs. In terms of the carbon, okay, we do need that pool in there. In terms of the carbon, my back of the envelope calculations looking at, for conifers, looking at how much the weight of cones that are produced, the weight of pollen that are produced, whatever, is that the amount of carbon that's involved here is probably less than 5% of the total carbon.
Okay.
So I don't think it's going to make a big difference to the stem width, for example. But it is going to make a difference, I think, to how much pollen you see on the landscape.
Yeah, I mean, that's where I was trying to link. Then
Yeah,
your
yeah.
cover model is going to be wrong.
So that's right.
Okay.
So that's something I really would like to work on, Graciela. So
Okay.
we need some modern observations about pollen productivity, fruiting, what climate controls it, etc., etc. And then we need, and how it relates to CO2, and then we need to put it specifically in here and tune for it and come up with what might be happening. So yes, we will do that.
Okay.
Well,
Good.
We will do
Yeah,
that.
sure. Yeah.
That's why I'm here.
It's a
We will do that.
It's a real pity that some critical people is not here today.
Yes.
I'm thinking
No,
of
no.
Sarah Palacio. She's
Yeah, we'll be
worked
back.
a lot in allocation.
Yeah.
So,
Yes. No.
Yeah. Okay.
No, but I mean, this is
Yeah.
the start of a conversation that I want to keep having, so we'll
Okay.
do that. Okay. Now I wanted to ask this question. How on earth is it possible to reduce your root mass by 30% and still survive in California, right? And it turns out that the reason it's possible in California is because, in fact, the climate was cooler and wetter at that stage. So, again, California at last glacial maximum, huge lakes, not tree vegetation, but some trees there, but huge lakes, and essentially it's because the westerlies were being rerouted around that Laurentide ice sheet and they were pouring water onto California. So something like 200-300 millimetres more than they get today was coming in there. It was also about 5 degrees cooler, and again we have independent evidence for that. And so then we can say, okay, is that what makes it possible? So here's again another nice thing with a model, you can do some experiments. What we've done here is to start with the LGM conditions and then systematically change each of the climate parameters. So this is atmospheric humidity, precipitation, the temperature and precipitation together, all three together, and then I'm not quite sure what else was in full, but something else was added in full. Maybe it was clouds, possibly clouds. But anyway, I mean the point here is that you can then say, well, what of those climate changes, wetter, cooler, you know, more cloudy, whatever, would have explained what was going on. And you see it's really this temperature lowering that enables the trees to survive because they actually have less of a demand for water, and the precip also helps a little bit, so having more precip will also mean that they don't need as much roots to survive. So this is how they are actually managing to survive. So what I'm doing now, this is the first step, we do that photosynthesis part with the P model, and I can run the P model spatially. This is just a simulation of the last millennium using one climate model. So this is an IPSL model. We've taken the climate outputs from that and I've run it through our thing, and this is what it predicts for GPP. You can see here increased GPP in the medieval warm anomaly, reduced PPP during the little ice, GPP during the little ice age. So it seems to be behaving relatively well. And I wanted to make the point that we can look at the correlations with individual climate factors in this simulation over the 1,000 years. So this is the correlation with light, with cloud cover, with mean temperature during the growing season, and with atmospheric drought, so VPD, deficit. And you can see that the factors that influence growth over this period vary. The strength of the correlation with each of those factors vary. So obviously PAR is really important, and it turns out that it's maximally important in the far north and less so down here. Cloud cover is relatively unimportant compared to this, but changes in cloud cover obviously have an impact in China and an impact in this central part of Europe. The changes in temperature have spatial patternings as well. Temperature always has, when temperature on its own always has a negative effect in this region on tree growth, operating because it increases drought essentially. And here's the evidence for that. Here's the vapor pressure deficit. You can see the patterns of strong influence of vapor pressure deficit. But also, you can see that over this, even over this time period, there has been a strong influence of CO2. So even though the changes of CO2, pre-industrial changes over that millennium were 10, 12 ppm only, 15 maybe a maximum, you can see that that has had a role on GPP growth in Eurasia, stronger in areas which are arid or more arid than they are in the high northern latitudes. So here we have another evidence of this multiple control on tree growth. And you can see the next thing I'm going to do is to start plugging that stuff into the tree model for direct comparison with the tree limits. So take-home messages here. The first thing I want to say is it's not age that affects tree growth, the rates of tree growth through time, it's actually the size of the tree. So if your tree starts off doing badly, it's going to have smaller tree rings all the way through its life. I also want to emphasise that, as we know, as any ecologist will know, that growth is controlled by multiple factors, multiple climate factors and non-climatic factors, and the relative importance of those factors will vary through time, so you cannot assume stationarity. I also want to emphasise that plants are actually clever, and they are basically optimising their growth for any conditions. So they are buffering extreme climate changes or extreme CO2 changes by changing allocation. They're trying to get the maximum they possibly can out of the environment. This means that when you look at tree ring variability, it's going to be much less than climate variability. Which is why, if you put a volcano into a climate model, you get a big drop in temperature and the tree rings don't show it, I think. And the other thing is just to say, you know, trees aren't foresters. A forester goes out there and he wants to maximise the amount of wood harvest he's got, because it's the timber that pays for forestry. The trees don't care about the timber. They care about the leaves, and they care about the nutrients and the water. So that means they're maximising leaf cover and root cover, and just keeping the stem as much as they actually need to get water and nutrients to flow up and down. We forget that because we keep thinking they're going to be the same. So this is my Martin Luther moment. I know that's probably not appropriate in Spain, but we did live in Jena where he had big arguments at the university. And I also did my PhD in Lund, where they still nail your PhD thesis to the cathedral door. So whenever I'm at a point of really challenging the community, Martin Luther appears. So here I'm going. Number one, statistical reconstructions from tree rings are fatally flawed. They are wrong.
Oh, you are going to love Gabriel.
I'm going to have lots of fun.
You are going to love someone from this institute so much.
Good, good.
On Monday.
On Monday,
yeah.
we'll talk about it.
And she's going to love you too, I think.
Good. But I really believe that we're putting a lot of effort into making these reconstructions and not putting a lot of effort into ecologically understanding the thing that we're reconstructing from. I do not believe statistics get you very far unless you have conceptual knowledge of the system you're working with. Okay, we've got a model, this productivity and tree growth model. It's based on this idea of optimum allocation, and it does simulate tree growth mechanistically. Now, it's not perfect. We haven't got non-structural carbohydrates in there, we haven't got reproduction, but we could work on that and put it in. but it does give you a tool to start making these explanations and saying, what if we do things? And I think we should be, as both paleoecologists and ecologists, doing a lot more what if work with models. So let's do this. And then again, I'm sticking my neck out here, so this is my research agenda over the next 3 years. We can use that model to make formal investigations of paleoclimate records and say what could have explained this, and I've shown you the example from the Bria. But the other side of it is quite a simple model, and ultimately we can turn that model, we can invert it, and we can come up with better founded climate reconstructions. That's where I want to be. That will endear me to all of the dendro community. Thank you.
Thank you. Excellent talks. Thank you very much, Colin and Sandy. It's true that it's a pity that both dendroecological and taphonomical or ecological taxonomy groups are not here today. Both are in field work, but I'm sure that next Monday they will be really interested in all these ideas. And in respect paleo, what can we do with palynological interpretation and a correct consideration with the CO2 effect? Because almost for recent periods, I don't know how to consider what is the role of CO2, what is the role of global warming, and what is the role of human changes in the landscape use, you know, the abandonment of high mountain areas, all these causes can be related with the forest expansion. So what is the most important thing, the mix of the different possibilities? What is the main protagonist? What do you think? CO2?
I think on glacial interglacial time frames, I think CO2 changes are really important in driving the vegetation.
Yeah.
I also think they're important in driving the current changes. I think they're probably more, I think in the past, I think climate was really important, but probably that's on the sort of shorter millennium time scale. I think you'd see climate fluctuations having a really big impact. At present day, I don't think we've seen enough climate change to have an impact on the vegetation, a serious impact on the vegetation. I mean, it's impacting the length of the growing season, and a little bit on the productivity maybe, but I don't think it's moving stuff around yet, because we just have had a comparatively minor change since the pre-industrial.
What about abrupt changes in the past? Really short.
Well, if you're thinking about things like the Dansgaard-Oeschger events, I mean, there's a big changes, but they're CO2 and climate together.
Yeah, but the CO2 change is quite small during the Dansgaard-Oeschger event, so actually abrupt climate changes give you sort of a test, because you don't expect 20 parts per million change in CO2, you don't expect a very big effect, but you have, if you're warming by 5 degrees or something, you do expect an effect. So over the, it's actually, I mean, it can be done. What's that? But that's correlation, is it? Or?
That's the correlation, but I do not remember what the. But I mean, here we're talking about maybe 12 maximum 15 ppm, and this is the amount of. So this is GLM correlation values. So this is the amount of additional CO2 from that CO2. This is the amount of additional GPP from the CO2 change. So I don't think the CO2 change is negligible, even over the Dansgaard-Oeschgers. I'm not saying it's the most important thing, but I think it's small, but it's still there. But in a sense, what you're saying is that that's why in a model world you could actually test what the relative importance of CO2 changes in abrupt change were compared to the climate changes. and then you're saving your paleo data as a test.
Yeah.
Of that. You know, it's like, do you
Yeah.
need to have CO2? It's like the experiments that Colin was showing. Do you need to change CO2 to explain the observed LGM patterns or the
I think the
observed
point
gas
here,
oil?
if you just compare, you know, a long, you know, let's say several thousand year period around the LGM, and then you compare it to the whole late Holocene, basically the climate that you have over that long period roughly is in equilibrium with CO2. Right? So that all of the global warming has happened, right? Because it's had long enough. Whereas at the present day, because we're increasing the CO2 fast, so fast, that the climate is actually out of equilibrium with CO2. So we haven't seen all of the global warming that will result from the CO2 that we've got now, right? So as Sandy said, we actually haven't had much climate change. We haven't had as much as you would expect. We're going from 280 to 400 ppm. But I think it's the same in the Vegetación event, because of course the whole system was out of equilibrium, right? So you know, you're seeing a climate. It was the other way around. The climate change is much larger than that because it's caused by something nothing to do with by a phenomenon that has nothing to do with CO2. So I think all those cases are different.
The comparison of them
But
should
by
enable
comparing
us
them,
to
you actually should be able
start
to find something.
taking,
You should be able to
taking these
test
patterns
some of these
apart.
ideas.
Yeah.
Is there any place, it's very interesting the comparison with the last glacial maximum. Is there any place on Earth that we have trees from the last interglacial, that they are preserved, that we can measure that do exactly kind of the same as you did with the last glacial maximum and see what happens during interglacial? Are they preserved?
So there must be in Alaska. I haven't thought about that. One of the ways they know where the trees were at last interglacial is that they were right up against the Arctic border, and that's because they've got preserved tree stumps. But I don't know whether anybody's actually looked at it from a tree ring point of view.
And what would you expect? Those tree rings to be wider? Or
Well, actually, one of my first question was going to be to your talk, and then you have answered in yours, is whether wood vegetation can storage CO2 forever, unlimited. Is that possible? That's something that we have to, I think of somehow. It's like, of course, again, we don't have anything to test against, but possibly the previous interglacial. To see, because I don't know whether trees can, physiologically storage CO2 forever, or just like keep it forever and then take it when CO2 reduces in the next glacial time, or I don't know. It's a more
do we know
possible
if
question.
trees were bigger during the last interglacial, the same species?
Tree ring. I don't know.
I
At
don't
all.
know.
I don't know at all.
We do, however, have evidence for changes in global land carbon storage. So I mentioned briefly that one way in which you can use delta C13 is that I didn't go into it, but that we do know that the delta C13 in the ocean was actually, the carbon in the ocean was actually slightly lighter during the glacial maximum. And you can actually calculate from that, knowing what the size of the various stores are, carbon storage, you can actually calculate a change in carbon storage between last glacial maximum and present. It's about 400 petagrams. It's a bit less than we modelled. Maybe reasons for that. I won't go into that, but it's
So
a bit less than
400
modelled.
petagrams compared to what's the standard now?
So compared to, recent times, we won't actually say now because of course we've had deforestation and so on, but compared with late Holocene. So the terrestrial biosphere was storing about 400 petagrams less, and that phenomenon we basically can simulate, and it turns out to be the effect of CO2. It's not due to land area change, it's not due to climate change, it's due to CO2.
But then
So you can have changes, you can have increases as well, but we don't know much about the last interglacial situation.
But 400 petagrams, how much is that as a percent of
Well, so if you exclude the carbon in permafrost, so this is where it starts to get complicated. The carbon stored in permafrost soils and all of that area there. If you exclude that, then total is about 2,000 petagram, so it's like about...
So 400 is about 20% or something
Yeah,
of
it's
the,
quite an amount, yeah.
of the total.
Now, that's total. Remember, that's not all in vegetation, though. In fact, more of it is in soil. That is actually vegetation. So that, to my mind, that's the place you would look for for long-term carbon store. Is in the soil rather than in trees, and it's very controversial actually how much can be stored and for how long in vegetation. But the soil is another matter, because as you increase productivity, you increase the amount of litter production, and then a certain amount of that litter ends up as long-lived soil again.
So, I mean, I wanted to ask a question to you guys in a sense. One of the things that has been intriguing me, thinking about carbon storage, is the sort of sense in which the really long-lived trees are in the more arid environments. Thinking about this Atlantic cedar, which can live 1,000, 1,500 years, or the giant sequoia. That you're getting onto the margins of where trees are. So why would you be long-lived in what must be a marginal environment for tree growth?
Well, certainly because of that. Actually, I would think that's the very... I mean, you take a bird, and that's a very pioneering species, right? I mean, it's a species that is going to grow as soon as there is an open place and we have water enough, and then it grows very fast and it doesn't last. I'm not a tree ecologist at all, but that's from my very seminal knowledge what I would expect. However, if you are living in a very harsh environment, and we have people here doing PhDs in harsh environments, you grow very slow. You integrate carbon in a very slow manner, because you never know what's going to happen next year, whether you're going to have water or not, and then you are resilient somehow to whatever it happens, and then you live forever.
But then you have to put up with these quite. I mean,
very
once
large
you go,
in time, yeah, in time.
But once you go back into those marginal environments, you actually also have more inter-annual variability, right? So you're having to survive for decades. So slow growth over decades. I mean, it doesn't that say that you're adopting this buffering kind of environment?
Also,
I mean, because we normally think about it in terms of succession, fast-growing trees, use the resources quick and whatever, and slow-growing trees use resources more carefully.
That's one.
But it's got to sort of tie into what you might experience.
And also something you said that I think is critical is evolutionary traits. Conifers are very old things. Say sequoias are conifers, pines are conifers, and they grow in, again, harsh environments. So somehow you have that trait implicit in your genotypes. From
there has to be a reason for selecting the trait. I mean, I'm just interested in this whole issue of the relationship between difficult situations and climate variability, and maybe this relates to the things that you were talking about, Penelope, at your talk about resilience. You're actually almost saying, well, the long-term variability is what would favour resilient species, or if you see resilient species, maybe that's telling us about long-term variability. I don't know. Just a thought.
It's telling us about droughts, actually, because to be resilient to droughts, a tree has to have wood that can withstand very exactly it can avoid cavitation, that will withstand very low water potentials. I mean, the inter-annual variability comes into it in the sense that that droughts, environments where drought is common, often have they have a lot of variation, and they can have like 10 years of drought.
Right, but this is what I'm concerned about, is this long-term drought.
But I think that probably the slow growth probably has to go slowly, because it's having to keep its tomatoes shut most of the time. It's going to probably grow slowly, but also it has to have this very safe wood, right? Which is safe wood is it has these very small, very narrow conducting elements. So that's probably one reason why it's usually conifers that you find at the margins of trees.
Maybe from the perspective of the model, it would be better not to look for really old trees, because those are the ones that, if you want to do dendro, then you're trying to find the oldest tree ever. But maybe the trees that they're going to record better, not just one particular aspect of climate, but a general model, it would be something that is going to live only for 100 or 200 years. So maybe that would be better to think about other kind of trees and not this all resilient. This is a geologist speaking, so I have no idea what I'm talking about.
No, I mean, we do want to try applying this to broadleaf trees as well. So it'd be interesting. I mean, it's almost by accident that we've done 4 conifers in a row, as it were.
But dendro people like conifers, don't they? Because they produce nice round rings, right? They're not going to misshape them.
Yeah, but I think we could apply it to broadleaf.
And another, when you were talking about this divergence at the very end during the last 30 or 40 years, is there any difference between different regions and between different trees? You show a few examples. There are some places that divergence is smaller than others? Or
there's some places where it doesn't show up at all.
And that's where in the tropics, or
no, it does show it. I mean, so the tree rings in the tropics don't seem to show any change, and the implied relationships would suggest that they do. It seems to be very site specific. So some sites in the Arctic, some sites in the tropic show diversions, and some don't. And that's why there have been all of these, you know, what is it due to? Because theoretically, if CO2 is having, well, if climate only is having an impact, then you should see it, you know, you shouldn't see it anywhere, or you should see it everywhere if it's a CO2 only effect. But if it's a playoff between CO2 and climate, then that could explain this spotty pattern, I think. So I mean, our first site, you know, the Chiangbai Mountains, we didn't see the divergence effect. We were able, you know, the climate relationships go all the way through. Great Western Woodland, we do see it. So it is not clear.
No? More questions or comments? No? So thank you very much. Thank you. And, it's lunchtime.